So converting between units is pretty simple. You just have to treat each unit like a variable in terms of the other units. So if you have uh 10 miles per 20 minutes. I'm just going to go over one of the sample problems in the book. So you travel 10 miles in 20 minutes, which is a unit of length and a unit of time, obviously. What is your average speed in meters per second? So the average speed is defined as the length, the change in length over the change in time, which is going to be 10 miles per 20 minutes, which is equal to 0.5 miles per minute. So what this is giving us 0.5 miles per minute, so it's giving us a value that's in units that aren't that useful. So what you do is you treat each of these like a variable. So 1,609 meters is equal to 1 mile. And 1 minute is equal to 60 seconds. So you relate these variables to each other. So 0.5 miles per minute is going to be 0.5 times 100,609 meters per 1 mile times a mile times 1 minute per 60 seconds times 1 times a minute. So you see how we're allowed to do this, right? Because 1,609 meters per 1 mile is equal to 1. Because we just go 1,609 meters over 1 mile equals 1 mile divided by 1 mile is equal to 1. So we're allowed to multiply by these values, 1,609 meters per 1 mile and 1 minute per 60 seconds. Because they're both equal to 1. Oh, and this is 1 over minutes. So they're both equal to 1, even though you have these different units. You have minutes and seconds, and you have miles and meters. So this is going to be 0.5 times 1,609 meters over 60 seconds, which is going to be about 13 meters per second, because the miles cancel out and the minutes cancel out. So does that all make sense? That's how you do unit conversion? Does that make sense?
But we just have to cross multiply, Professor.
Cross multiplying. Oh yeah, cross multiplying is just how you get it equal to 1, yeah. So that's how you find how many meters are in 1 mile. Or you find how many meters are in 1 mile and then you cross multiply to get those both equal to 1. And then you insert that value into here in order to cancel out the minutes and the miles. Okay, let's see, clear all drawings. And then dimensional analysis is going to be something similar to that. So in general, any physical quantity can be written, the units of any physical quantity can be written as length to the A, mass to the B, time to the C, current to the D, theta, which is a unit of temperature, to the E, N to the F, which is the units for moles. Even though moles aren't really units, I'm going to say, and J to the G, where J is the units of luminosity, which is the candela that we were talking about earlier. So it's just those fundamental units that we were talking about, those base units we were talking about, to some power. So the units of any physical quantity, these brackets indicate that we're talking about the units of some value. It's going to be just these variables, these basic variables to some power times each other. So the units of the kilogram are equal to L to the 0, M to the 1, T to the 0, I to the 0, theta to the 0, N to the 0, J to the 0, which is equal to 1, which means that it has units of mass. And the units of speed, meters per second, is going to be equal to L to the 1, M to the negative 1, or not M to the negative 1, M to the 0, T to the negative 1, I to the 0, theta to the 0, N to the 0, J to the 0, which is equal to L to the 1, T to the negative 1, which is equal to L divided by T, which gives us the values that we're going to expect from this. So meters per second is speed, so that's going to be the change in distance of the change of time. Kilograms is just mass, so that's just going to be mass. So that's going to just be how you do dimensional analysis. Or not even dimensional analysis, that's just how you find the differences in, or how you find the different types of units in terms of the base unit. So where's save? There it is. There are some rules about this that are very, 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 very useful to know. So the rules, I'm going to just steal directly from the book. So every term in the expression must have the same dimension, so it doesn't make sense to add something with the different dimensions together. So you cannot add 1 meters per second plus 20 kilograms together, because that doesn't make sense. So every term in the expression must have the same dimension. So you can add 1 meters per second plus 20 miles per hour, as long as you convert from meters per second to miles per hour, or miles per hour to meters per second. But you can't have this value where you have 1 meters per second plus 20 kilograms, because that just doesn't make sense. Because how do you add mass to a volume or to a speed? The second one is that the arguments of any standard mathematical function, such as trigonometric functions, logarithms, or exponential functions that appear in the equation, must be dimensionless. The functions remain pure numbers as input and give pure numbers as outputs. So you can't take sine of 20 meters. So what is this? Sine is a function that takes a number out. Or it takes a number and it outputs a number. So sine function of 20 meters, that doesn't really mean anything, because you're talking about units inside something that's designed to take a number. So what you have to instead write out this is going to be confusing for people who didn't watch the lecture, so I'm just going to write 20 meters per second. So what you have to write out is you have to have, instead of sine of length, you have to have sine of some value times length, which is going to be, for example, sine of 31 over meters times 20 meters, where 31 over meters is just a constant of the sine of the value, times 20 meters, which is going to give you sine of 600. So K in this case is 31 over meters, which is just a constant of the function in order to keep it unitless. So whenever you have these values, whenever you're talking about sine or cosine or exponentials or logarithms or anything like that, that take a number and output a number, then you have to make sure to have something like this in the function that cancels out the dimensions of the quantity that you're looking at. Okay, does that make sense?
Professor?
Yeah.
So when we're dealing with functions like sine or cosine, it always has to be, we always have to set it up so that it's just numbers and not measurements inside of the equation.
Yeah, so whenever you do, if you're just talking about, so sine of k times length is a did you do like wavelengths in calculus or algebra?
Yes.
So sine of k times length, the k just tells you some function of the sine that you're looking at. So it's the k is actually equal to 2 pi over the wavelength.
Right.
So it just has to have that value in there, and then that value is going to determine what the wave looks like versus length. So let's call this amplitude and length. So sine of something with long wavelength versus sine of something with a short wavelength. So it's just a property of the function that's going to tell you how it reacts versus this dimensionful quantity, even though it does have a dimensionless input. So you just basically always have to have that k in there, or you have to have some sort of constant in there to cancel out the length or the time or the length squared or whatever you have in your input in your argument.
Okay.
And then last thing about dimensional analysis is just that the units of dy dx are going to be equal to the units of y over the units of x, and the units of y dx, the integral of y dx, is going to be equal to the units of y times the units of x. So that's just something to keep in mind when you're doing integrals or derivatives.